Okay, this first session this afternoon is on correlations and comparisons. So we're moving from case studies into, looking at the dilatometer compared to other kinds of tests. And we have three authors on the schedule here. And first up is our Italian friend Paola.
So good afternoon, ladies and gentlemen. The paper I'm going to present now is a review of available experience, including comparisons between settlements predicted by DMT and measured in real cases. The paper was written by me and my colleagues at L'Aquila University, but really this paper was written by many people because it is substantially a compilation of the work done by others. And it is a compilation of documented case histories limited to the cases available to us, including comparisons of settlements calculated by DMT and measured. The intention was to review the available experience on the use of DMT for settlement calculation, for predicting settlements of shallow foundations, which is probably the best application of the DMT. An evaluation is made of the accuracy of settlements predictions by DMT, and the constrained modulus MDMT has been found to be a reasonable operative modulus for predictions based on the traditional linear elasticity approach relevant to foundations in working conditions. And attention is also made to the determination of a strain range appropriate for the constrained modulus MDMT in view of the possible use of MDMT for nonlinear settlement predictions, taking into account the decay of soil stiffness with strain level. Next, please. So some of these aspects have been already illustrated so far, so I won't give many details. Just to recall that the constrained modulus MDMT is the basic stiffness deformation stiffness parameter obtained from DMT, and the important fact is that this modulus is obtained from DMT measurements by using a correction factor depending on KD, the horizontal stress index, that incorporates information on stress history and horizontal stresses. And the necessity of stress history for a realistic assessment of settlements has been emphasized by many researchers. Many comparisons available, both in terms of comparisons of moduli from DMT and obtained by other methods, say high-quality odometers, and also in terms of predictive and observed settlements, have shown that this modulus is reasonably accurate and dependable for everyday design practice. Next one. And these figures have already been shown. This is a comparison between moduli from DMT and from high-quality odometers obtained by Lacasse NGI in Onso Clay in Norway. The next one is also already been shown, is the same comparison in Tokyo Bay soft clay in Japan. And this one is closest to this place, is a comparison obtained in places I think very close to where we are now by Feilmetzger and Bullock in Virginia sites. Next one. So the method for settlement calculations that we prefer to use is the traditional one-dimensional method based on the linear elasticity approach. In this method, stress increments are calculated by use of the classic elasticity theory solutions by Businesq, and the constrained modulus is obtained from DMT. As an alternative, if one wants to make 3D settlement calculations, it is possible to use Young's modulus obtained from the constrained modulus using the classic elasticity theory relation. And in general, the results obtained by the 1D and the 3D formulae are very similar. It should be noted that this linear elasticity approach provides a settlement proportional to the load and is able to calculate settlement in working conditions, say for foundations in working conditions, say for a safety factor typically 2.5 to 3.5. Next, please. Methods for calculating settlement by DMT were proposed initially by Schmertmann, who in '87, who proposed that this ordinary method, which is substantially the one-dimensional method that we prefer to use. And also he introduced a special method with the adjustment of modulus with varying effective stress during loading in the normally consolidated in the virgin compression and recompression range. But he also observed that the ordinary method is adequate in most cases. Another procedure was proposed by Leonard Frost in '88 for evaluating settlements of footings on granular soils, taking into account the effects of over-consolidation on compressibility by using coupled DMT and CPT results to identify the pre-consolidation pressure and using soil moduli obtained from DMT. This second procedure, I think, that is, however, less used than the one by Schmertmann. Next one, please. So the database that we have collected to investigate comparisons of settlement calculated by DMT and measured includes both Class A and Class C predictions. The cases range from well-documented case histories, including details on soil properties, foundation characteristics, and measurements, to semi-qualitative assessments of DMT predictive and observed behavior without quantitative data, and also simple comparisons between moduli or settlements calculated by DMT and by other methods. Next one, please. So I will show some of the cases that are illustrated in the paper, not all the cases. And of course, this is not a complete database. I think that it would need to be updated from time to time, also including some contributions here at this conference. This is an example of a good agreement found between moduli obtained from DMT and backfigured from measured settlements of silos, and also moduli obtained from screw plate and CPT in drum and sand in Norway, site investigated by NGI. Next one. This is the case, a case presented by Schmertmann in '86, which is probably the most complete documented case, including 16 case histories of concerning various soil types, ranging from peats and organic soils to clays, silts, and sands, and for different kinds of foundations. In general, the ratio between the settlement calculated by DMT and measured was found mostly in the variable in the range 0.7 to 1.3, and on average it was found equal to 1.18. That is a very good prediction. Next one. And this figure also was made by Hayes in '90 and includes also some of the data shown by Schmertmann in the previous table and additional data. And it shows a very good agreement between settlements calculated by DMT and measured for a wide range of settlements. Next one. This case was presented by Scalzi and Tauschen in '94. And they compared settlements predicted by DMT and measured in 11 load tests carried out on square footings in sand in controlled test pits. And the tests were made at 4 different periods corresponding to different values of sand density. And in this case, the ratio between the DMT calculated and observed settlements was ranging from 1 to 2.5 with an average values of of 1.87, showing in general a good agreement, but some over-prediction of DMT. Next one, please. Well-documented case is the Spread Footing Prediction Symposium, which was held at Texas A&M University in 94 in connection with the Settlement 94 conference. 5 square footings ranging in size from 1 to 3 meters were constructed, and load tests were carried out on this footing at the Texas A&M University test site, consisting in medium dense siltified sand. And predictors were asked to formulate a Class A prediction of the load settlement behavior of all the 5 footings using data from several in-situ and laboratory tests. And various predictors used DMT for estimating the value of Q25, which was the load measured in the load test curve, corresponding to a settlement of 25 millimeter, say for a ratio of settlement with a foundation of 0.8 to 2.5%. Next one, please. And the average ratio DMT predicted that measured Q25 for all the 5 footings was mostly in the range 0.5 to 1.2, say within 30% from the measured value. And also an additional Class C prediction in this case was later made by Marchetti. And in this case, for the footing 3 meter size, the over prediction was 25% and 15% for a smaller footing. The data are summarized in this figure, which shows the predictions by DMT, that are the single points, and the curve is the measured load settlement curve for a footing having size 3 meter during the load test. Next one, please. This is a case of a full-scale instrumented embankment that was constructed near Venice, and it's a very important research project. I won't give much details about this because I will present a paper on this subject tomorrow. And in this case, the soils were highly stratified silts or silty clays and sands that are typical soils of the Venice Lagoon. And we were able to make a Class A settlement prediction before having the field measurements available. Next one, please. And this figure shows settlement time curve obtained measured under the center of the embankment. It can be seen that the settlement predicted by DMT at the end of the construction was 29 centimeters, while the measured settlement at the end of construction was 36 centimeters. And it was found that the measured settlements also include some significant part of secondary settlement developed during construction that in this case occurred essentially in drained conditions as demonstrated by piezometer readings. So in this case the DMT predicted settlement net of secondary, because the DMT is not able to predict secondary settlement, was 20% less than measured. That also includes some secondary during construction. Next one, please. This is a case studied by Paul Main, and it's a case of a large mud foundation of a 13-story dormitory building in Atlanta on Piedmont residual silty soils. Next one, please. And the settlement estimated by SPT was 46 millimeters, while the settlement measured at the end of construction was much higher, up to 250 millimeters at the center. And Paul Main explained that such incorrect prediction as due to an over-reliance on SPT data coupled with a poor choice of model used for analysis and other bad judgments. And he also showed that settlement calculated by simple elastic solutions with input moduli from DMT and finite layer thicknesses are in excellent agreement with measured settlement profiles. And if carried out before, would have warned the signers of these excessive displacements. This figure is taken from the paper by Main, shows a comparison of a settlement profile along a diagonal axis of the math foundations, showing a good agreement between the predictions and measurements. Next one, please. This case has been already, of course, illustrated yesterday in his keynote lecture by Professor Schmertmann. And the Cape Hatteras Lighthouse relocation has provided various comparisons of predicted by DMT and measured settlements, showing a very good agreement, as we have seen yesterday. Next one, please. Roger File-Metzger, I think, has produced a lot of contributions on this subject, mostly concerning the comparisons of settlements predicted by SPT and DMT, showing in general that SPT tends to over-predict settlements, and the use of predictions, settlements predicted by DMT can in many cases lead to change in design and cost savings, as shown also in this case this morning. Next one. And Roger File-Metzger also analyzed it in various papers the standard deviation of settlement predictions by SPT and DMT, and he found standard deviations for the for SPT about 3 times the standard deviation for DMT. Next one. And this, I think, this figure is a summary of what was intended in these various contributions, showing that the comparisons of settlements predicted and measured by SPT and DMT shows that the SPT predictions are much more scattered. And this is the SPT database is the database by Berland and Barbridge. Next one. And there are various contributions on comparisons of pressurometer and dilatometer, and in general various studies have found a good agreement between a modular settlement evaluated by the 2 tests, but various authors have indicated that the time for pressurometer testing is about 4 times the time required by DMT, and also the costs are higher. Next one, please. So there are many other contributions that are mentioned in the paper and other that need to be added subsequently. Then this figure is a summary of available comparisons of settlements predicted by DMT and measured. This figure includes over 40 data points taken from the case history I have mentioned, including numerical data. And it can be seen that in general we have a good agreement between settlement predicted and measured. And this agreement applies to a very wide range of soil types, because it includes from organic soils to silts and sands, and for a wide range of settlements ranging from a few millimeters to up over 300 centimeters. And also for different width of foundations, because it includes small footings, but also large rafts and embankments. Next one, please. And the average ratio between calculated and observed settlements for all the cases was 1.3, so this is a very good results. Also the band amplitude between the that is the ratio between the maximum and minimum is less than 2. That say the prediction is not more than 50% far from the real value. Next one. So the global experience from several case histories has indicated that DMT is provides, coupled with the linear elasticity, provides a reasonable accurate settlement predictions for foundations in working conditions, say for safety factor 2.5 to 3.5. And so MDMT can be considered as a reasonable operative modulus. And current research investigates the possible use of MDMT for settlement predictions based on nonlinear methods, taking into account the decay of soil stiffness with strain level. And the objective is to develop methods for evaluating in-situ decay curves of soil stiffness with strain level, like G-gamma or similar. And the aim is to derive tentatively G-gamma curves by use of the seismic dilatometer by fitting reference laboratory curves through 2 points. The first point is the initial modulus G0 from shear wave velocity measurements. And the second point is the modulus at operative strain corresponding to MDMT, but provided the strain range appropriate to this modulus is defined at least approximately. And, some preliminary indications about where this strain range could be located has been given by previous studies. This figure by Main at the Bali conference indicates a possible gamma strain range for the MT modulus from 0.5 to 0.1%. And a similar indication was given in the same conference by Ishihara, who located the DMT within the group of methods at an intermediate strain level. Next one, please. In most of the cases that we have analyzed, the MDMT predicted well settlements for a ratio between settlement and width of foundation S over B, mostly in the range 0.5 to 1%. And this information may help for deriving in-situ curves of decay of soil stiffness with strain level from the seismic dilatometer that could be, for example, expressed in terms of decay of the Young's modulus over the ratio relative settlement width of the foundation. Next one. So in conclusion, the available experience indicates in general satisfactory agreement between settlements predicted by DMT and measured. And in most cases, the MDMT proved to be a reasonable operative modulus for foundation in working conditions. And as stated by Poulos at the Istanbul conference, methods for estimating settlements of footing can be evaluated in terms of 3 parameters, which are accuracy, let's say the ratio of calculated to measured settlement, reliability, that is a percentage of cases in which calculated settlements were greater or equal to the measured settlements, and ease of use, which is the time required to apply the method. And based on the available data, the DMT proved to be able to predict settlements with general satisfactory agreement from all the 3 above points of view. Thank you.
This presentation in some respects could be called the effects of construction. But anyway, if you look at the dilatometer test, it provides high quality mini load test at each test depth. Marquette has talked about this. People want to argue about whether horizontal or vertical. In this case, you're applying a load in the horizontal direction, and so is the lateral loads. There's no dispute there. You have a nearly continuous profile of data, and the DMT provides all the data required for PY curves, and therefore the DMT is ideal for lateral load analysis. It's certainly a good tool. One of the things I want to do, and I want to introduce it earlier, is I want to propose modifiers for PY curves. Now, in the paper that's in the proceedings basically uses the Robertson-Campbell method. But if you use any method, this same type of approach really, I think, is useful. And the first modifier is a modifier of lateral movement, and that's basically an offset that you have before you have any significant buildup of load. And then there's the CP, which is a modifier of lateral load. This modifier of lateral movement, this modifier of lateral load. These are multipliers. And this delta Y is offset that I was talking about introducing to account for zero load movement, or close to zero load. So why are these modifiers necessary? And the main reason is construction. And we have very little information on the effects of construction on lateral loads. Some years back, we started realizing that construction had an important effect on vertical loads, for example, for drill shafts especially. And we're beginning to get some information indirectly and directly on the effects of lateral loads on construction. So let's look at some drill shaft examples. If you look at the casing installation methods, yeah, they could have an important effect on lateral capacity. And I think it's pretty easy to see if you were driving a pile of vibratory hammer and you were in loose sand that this vibratory hammer is going to tend to compact the material around the pile. So it could increase the lateral resistance in sand. Now if you use an external flush, that may decrease the lateral capacity. And I want to show you an example that was presented by Fred Reimer at the DFI meeting in 2005. But this is from the World Trade Center, Building 7. And look at the movement that they had before they really started building up any load. And the reason for that, the external flush method, the water comes up along the outside, so it basically opens up an annulus on the outside of the casing. So that was the reason why I say that maybe we need a delta Y that we could put in here for an offset before we start building up load. Let's look a little bit about time effects on drill shaft sidewalls. When you open a borehole, you have soil relaxation, you have softening of sidewalls, you have slurry buildup. And this is from O'Neill's Tizargi lecture in 2001, and he basically measured the shear wave velocity at different distances away from the edge of a borehole. So this is radius of borehole, and you can see that it gradually increases, that it becomes constant out here. And so this would be 1, 2 out here at about 2.5 radii. So if you take your dilatometer test or whatever type of test you're using out here, you're certainly going to have a different strength than you have if it's over here close to the shaft. In fact, O'Neill estimated that the shear strength at this point right by the sidewall of the shaft is about 50% of what it would be out here. Let's look at the rate of softening. Depends on soil type, permeability, type of drilling fluid, and seepage forces due to the head differential. These are some data from 2 different sources, one from bentonite on a research project in Australia that Jim Holden was involved in, and they basically had a shaft that was open for a long period of time, and he measured the buildup of bentonite over a period of a little better than 16 days. We had a job in South Florida some years back that, the results were presented in '85 in a report, that we had the opportunity to measure the buildup of attapulgite on the sidewall of the shaft. And the way we did that, we took sidewall samples at different times and measured it. Does this really occur? Well, these are some examples from the job in Australia that they did some directional boring right down by the side of the shaft, and this dark seam that's here is bentonite. So that's bentonite that's left in the hole between the rock and the concrete. So you don't scare all that material away. And let's look at this picture. This was a shaft that was open for a long period of time, and they pumped it down, and this is the way it looked. Now this is a groove that was cut into the bentonite buildup, and look how thick it is. So you can imagine that this would basically introduce a delta Y that you'd need to have a good correlation with a lateral load test. Let's look at time effects on lateral resistance of drill shafts. Basically, result in a decrease in lateral resistance and an increase in lateral movement. Let's look at what happens at the bottom. You have all the same things at the bottom that you have on the sides, plus you have sedimentation of suspended materials. Now, sedimentation can have an important effect on lateral resistance, and that's especially true for a short shaft. Now, this is a case that you had a lot of suspended material at the bottom of the shaft. You end up with a bullet-shaped nose shaft, reduced end area. This would have been mud, this part that's missing out here. So if you had a short shaft that was just socketed into rock a short distance and you were counting on this basically providing a toe, you'd have a certain amount of rotation before you'd really start building up resistance. Let's look at possible result of time effects on lateral resistance, especially for short shafts. So decreased lateral load and increased lateral movement. Let's look at an example now from piling. The method of installation of piling could also have an important effect. And these are some model studies. This is some unpublished data from a study that Dr. Spurp and I did on a project in Jacksonville. And we're installing piling in close proximity to existing bridge. In fact, some of them were driven beneath the existing foundation. And someone had specified very widely, by the way, that they were going to jet 8 feet below the tips of these existing foundations. We didn't want to do that. But anyway, we did a model study to prove that it wasn't wise. So these are some results. So this is SOD, that space between the jet and the pile. And then this is ratio of the after divided by the before capacity, before jetting. And you can see, of course, if you jet a pile and you have, you jet it and it basically penetrates under its own weight. So at this point, you have no resistance. And then when you get out here at 5 diameters, the ratio is about 6/10. And you have to get out something around 25 diameters before the effect becomes insignificant. So if you take your sounding, let's say here, and you jetted a pile in, and you certainly could expect some decrease in strength and increase in lateral load or lateral movement if you had an effect like this. Now, when you drive a pile, of course, you have some reconsolidation of the sand. Go ahead. Let's quickly look at a case history, and this is from Rio Porto Nova project. It's in Puerto Rico. It's a Corps of Engineers project. And they had they put in some drainage to keep San Juan from flooding during storms. And they have these streams they call rivers that are about 60 feet wide. And they're widening these channels, and where they go under existing bridges, they're having to underpin them, and they're also, when they go by structures, they're having to put in retaining structures. And this was a test program basically to evaluate 48-inch diameter pipe piles as king piles. Let's look at the dilatometer testing. Used a drill rig to push with. So here the guys are doing the test. You saw this yesterday. This is the contractor coming to site. This is San Juan in the background, and right over here is a landfill that's about 150 feet high, say 30 or more meters high. The piles are instrumented. The contractor wanted to drive the piles initially, in fact, as far as he could with a vibratory hammer. Now, if you were driving in sand, you could expect some change in your measured values, measured soil values, before and after the driving the vibratory hammer. But the predominant soils at this site were clay, but anyway, he wasn't able to drive very far. Before he had to use a diesel hammer, well, he proposed using, that's what he did, to use a diesel hammer to drive them the rest of the way. We had a lateral load test, one. By the way, there was a little bit of excavation before the first test, and I'm going to call that the before excavation test because that excavation was relatively minor. But this is a jack. We had hemispherical bearings. There's a cap on each pile. There's a strut between them. We had a jack with a long stroke. We had a load cell that measured load accurately. So here was the other end of the strut on the other cap. And these are results. We did, first first static test at this level, and we did an unload and a reload, and we had a short pile and a long pile, and the long pile was about 20 feet longer than the short pile. Now, I know of no reason that the short pile would have more resistance than the long pile, other than maybe just site variability. There's a little bit of difference. Now, by taking into account the effects of excavation, we're able to get good agreement between predicted and measured by basically using a multiplier 1.1 for P. So that was a P multiplier 1.1. After we completed that test, by the way, there are also some stat dynamic tests, which I'm not going to go into, but after the testing was complete with at the first level, we built a cofferdam and we excavated the cofferdam down about 6 meters. This was a lateral load test after the deep excavation, and one of the things I want to point out, by the way, this is a platform that's built inside that's supported on the wales for the cofferdam. But we had wooden reference beams, of course, weather protection. The piles were instrumented. We had inclinometers that we could measure the deflection with depth in the piles, and it was a pretty closely controlled test. But well, here's the jack. I mentioned we had plenty of movement. We had a jack that would move, actually had about a 36-inch stroke, so we could move it out as far as we needed to or wanted to. But what I was going to say about the excavation now, what do you do about the excavation? How do you take it into account? Now remember that we excavated 20 feet of material. Now, the curves of the measured data and the points are predictions with an adjustment after accounting for the excavation. And one of the things I wanted to remind everybody, if you remove the upper soil, all engineers ignore it. You know, basically they treat it as it has zero strength. But what about right below the excavation? What do you do about it? Well, there's some effect of the excavation on the parameters that you measured before excavation. So this particular paper in the appendices, I attempted to account for the effects of excavation on all the parameters that are used in driving the values for the critical Y and the P ultimate. Now, this test was carried out with pretty large movements. Most of the published data you see, people are trying to match this part of the curve. But in this particular instance, we certainly got out to the PU, in other words, the ultimate, and we got certainly beyond the critical Y values. Well, with a multiplier 1.2 for P, we got a pretty good agreement with the long pile. Now, the short pile, we could have gotten better agreement if we had put a load at the bottom, maybe to simulate the shear on the bottom of the shaft or the bottom of the pile. But we were right at the verge of a rotational failure in this particular pile. And anyway, I thought it was important to do as little adjustment as possible, but anyway, to demonstrate the point. So I think we have pretty good agreement, and our comparisons with slope inclinometer information down the pile also compared well with these relatively minor adjustments, provided you take into account the effects of excavation. This is site after it's cleaned up. You can see a little bit of the edge of the landfill over back this way. But they're going to put in a wall all along here and a wall about 400 feet over to protect these structures. And there are a lot of walls to be built down on this particular job. I'd like to acknowledge the Army Corps of Engineers. It was their project, and of course GPE. And I'd like to answer any questions if I have time.
We have also performed some of these lateral load tests in Porto in our residual salt, and we have also this interesting question that is the same conditions of execution, drill shaft. The longer pile systematically is stiffer than the shorter pile. Although the soil is the same conditions, the DMT are very similar, and I think when you do the numerical analysis, the deflection is well above the base of the pile. Do you have any reason for this more stiffness in the highest stresses on this type of piles?
In the high stressed area, you talking about up near the surface?
Sorry.
I guess I don't completely follow your question. We had a case that I said that we had basically more movement in a long pile than we had a short pile.
And the other is the opposite.
So I didn't really see any reason for that unless it's site variability. We know we did have some site variability. Now you've had the opposite experience, is that what you're saying?
The opposite one, yes.
Okay, well, yeah, it depends on the condition. If you have, whether it's a short pile or whether it's a long pile. And of course, if you have let's say you had an infinitely long pile, then the tip wouldn't move. And you wouldn't be stressing the soil much down at the tip. But if you have a short pile and the whole pile is trying to kick over, if the material is weak down at the tip, well, it just rotates as a unit rather than bending, rather than deflecting as much. So it depends on the relative stiffness of the pile.
Yeah. Anyway, we have all this instrumentation through inclinometers and extensometer. We did not have this rotation in the base. But anyway, it's not clear the reason why it doesn't behave similarly. For what I understand, it's not reasonable. That must be variability only.
I can't think of any reason that. First off, if the long pile is anchored, then it's going to behave differently than when it rotates, like in this particular case, after the excavation.
Yeah.
But
anyway, okay.
Maybe somebody else can have a better answer for you. Any other?
Thank you very much. Well, our next author, Dr. Paul Main from Georgia Tech, started with the dilatometer some 20 years ago, not far from where we're standing right now. And one of the first efforts that he made was to correlate dilatometer and SPT results, which I'm sure he's fairly embarrassed by at this point. But today he will talk about the cone penetrometer and the dilatometer together. So,
Thank you, Paul. Sometimes it's good to look at some interrelationships amongst some of the in-situ tests that we use for site characterization. So today I'm going to look at the flat dilatometer measurements P0 and P1 in comparison with its sister, the cone penetrometer, and the measurements U2 at the shoulder, the pore pressure, and the tip resistance QT. And why would I do that? Well, way back we had some work with Dick Campanella, where they built a special research dilatometer. It was able to measure pore pressures right in the middle of the membrane during the insertion process and also during the inflation process. We have this now on demonstration. We have a little display center for the flat dilatometer down at Georgia Tech, so that if I'm unable to take students outside, I always like to take them out on a nice rainy, cold day. And if that's not possible, we just stay inside and look at the equipment here. And so the data that Dick Campanella showed in the international conference was a measure of the full pressure versus the deflection curve. And so we have a curve where the membrane's going up. We measure the pressures during the inflation and then deflation. You also have that pore pressure sensor. You see that's that dashed line here. You're going to have to click through here. And so P0's the beginning here. P1's the full loaded at 1 millimeter in this case, and then the unload, which they call P2. And they said, well, gee, that's P2's pretty close to the insertion pore pressure, the UI. So let's say that P2 is a first order measurement of the initial penetration pore pressure. And then I sort of have geotechnical eyes. I always have to explain this to my structural engineering students because, you know, they're into the perfection of things to 3 and 4, 10 decimal places sometimes. I said, well, gee, in a geotechnical person's eye, P0, P1, and P2 are essentially all the same reading, plus or minus a few percent error. So let me just say that P0, the red dot, is pretty close to the measurement of the blue dot. And so we went back and looked at that, and we compared data where we had penetration pore pressures from a piezo cone compared with the flat dilatometer liftoff pressure P0, and you can see there's sort of a relationship there that as the material goes from being very soft clay to firm clay to stiff clay to some of the harder clays, there's definitely an increase with those. And why would that be? Why would that be? That would be because when you take any large body of clay, very old clays that are thousands of years old and they're sleeping, and then you wake them up by jamming some sort of a probe in them, and that probe could be a pile foundation, it could be a cone penetrometer, a flat dilatometer, it has no idea what the shape is. It's just so surprised to be woken up after sleeping there for 10,000 years that you woke it up. It has no idea what the shape is at that instant of the penetration. And you can see that in some interesting calibration chamber tests that An Bin Huang did up at Clarkson University. He had chambers of kaolinitic clay that he had pressurized, and he had the chamber instrumented already with these little finger needle pore pressure transducers, and he took a dilatometer shaped blade and jammed it right into the middle. Of course, he knew the exact axis and where that would end up within that deposit of clay because he'd set the stage, if you will, you know. And so then he was able to measure the pore pressure isochrones. You can see they're all very symmetric during T equals 10 seconds. The first 10 seconds is the initial penetration. Everything's isotropic. It doesn't have any idea what the shape of that device is. It's just so surprised to be shocked by a penetrating object. Now, obviously, given some time, 100 seconds, 1,000, 6,000 seconds, it eventually figures out the shape. But during penetration, it doesn't know. So one way to explain this is that cavity expansion is one possible way of approximating both the cone penetrometer and the flat dilatometer, and I sort of wish Alan Littneger was here because I see he has a paper where he's using cavity expansion theory to explain some of the readings that he's gotten in flat dilatometer. So after we looked at this relationship in the 80s, I thought I'd go back and look at some new data that we'd collected, some new data from some of the national geotechnical sites. Just wanted to see, you know, was that trend still holding true? And what about the other reading of the flat dilatometer, the P1? Does that somehow relate to the QT reading on the cone? So I have these 3 natural sites. And then just before the conference, I dug up some old data that I had collected up in a chamber test up at Cornell University. So we have the Amherst National Geotechnical Site. That's a Varve clay. Bothkenner's a famous site. The entire June issue of Geotechnique is devoted to 15 papers about the site characterization of this national test site in Scotland. And then there's the NGS that is right off of Lake Michigan there, Northwestern University, but in fact, this site's just a little further away, right on the campus, and so let's look at some of that. Here's the Amherst site. The campus sort of sits up on the hill, and at the bottom of the hill we have some fairly thick deposits, maybe up to 30 meters of the famous Connecticut Valley Varve clays from Lake Hitchcock. Here's a little rig that Lutnegger uses there. He let us use it. It was rubber tired wheels at the time, and he's done a lot of foundation load tests. And I wanted Alan to be here because I think his test site's starting to look a bit like a cemetery, and I was wondering if maybe he'd kind of reserve a little monument there for me when I die. And so we went up there several years ago and did, I guess we did maybe 15 seismic cones, and so you can see there's some variability. There's a little bit of fill and there's some crust up here, and then here's the very soft Varve clay that I want to concentrate on, and then sleeve friction, pore pressure, and shear wave velocity. Okay. And we also did seismic dilatometers back then, and here's P0s, P1s, and arrival times of shear wave velocity, so we have some repeatability there. And so now let's compare the first reading here, which are the penetration pore pressures, and you can see this was back when we were doing a 50-50 glycerin water mix, and since then I guess we learned our lesson to go to 50%. Instead of 50-50 mixture, we use 100% glycerin, and that's helped us quite a bit. So only this upper reading is probably the best reading here, the dark blue line. These other ones seem to be slow in capturing as they go through this unsaturated zone. Good news is with the flat dilatometer, yeah, we're picking up the crust, of course, but we don't have a problem in the desaturation. And so that was something that was missing in our early study is apparently people are still having today, I'm finding out, pore pressure problems when they saturate their filter elements and keeping those saturated. With the flat dilatometer, you can see there's a really nice match between P0 and U2. I mean, that's extremely good match, but I have a problem with the piezo cone up here because it either got desaturated or my two graduate students who were up there were not doing their job properly. So, okay. And while we're there, let's look at the QT, which are the blue squiggly lines. That's the cone resistance. And they're just barely above the P1 reading, the expansion pressures from the dilatometer. So that's kind of interesting. There's actually some other reasons why I picked these three sites. I wanted to actually represent a wide range in the effective stress frictional envelope of these materials. And so now let's move to Northwestern University. We went up there a couple of years ago. We got a little bit of money out of the National Science Foundation. That's all they have these days, just a little bit of money. So it's kind of sad, present administration. In fact, right after this conference, I'm going down to 1600 Pennsylvania Avenue to talk to that guy, tell him to free up some more research money for geotech. So we went up there. This is the little truck we use. It's just a Ford 350 flatbed, but it has the full 20-ton capability in the back end. It has two twin anchors that allow us to tie that into the ground about 1 or 2 meters deep. And because of that, we go down about 30 to 40 meters. Because it's a very small truck, I don't need any special permit. Anybody in this room who has a regular car license can drive that truck. I don't have to stop at the weigh stations. I don't need to pay special taxes or special insurance. So I can turn this loose for the students, and there we go. And here's a bunch of soundings we did up there. This is the Ford Design Center, so it's a little bit, maybe it's about 100 meters west of the NGES, which is not really in service anymore, but we did sneak a few soundings down there. And you can see there's some fill and some sand layer, and here's that very, very soft, they call it a Deerfield till, but it's very, very soft clay here, the cone resistances, the sleeves, the pore pressures. Got one element on the face there that's a little higher than the rest because it's in a different position. Shear wave velocity profiles here using 1 meter increments, and then while we had the opportunity to work with Paola and Diego and Silvano, we were doing the seismic dilatometer in Tre Porte. We said, hey, if you're going to do A, B, and C readings every 20 centimeter, let's do the shear wave velocity every 20 centimeters. So we did that here. Every 20 centimeters, we have a shear wave velocity. See that smooth line going through there? It's nicely behaved. I mean, the shear wave velocity isn't this very step function that you see Roberts and Campanella and others show often. It's actually a nicely behaved profile. And it actually has a face. Actually has a real face. Okay, so now let's look at the pore pressures there. You can see, again, very, very nice agreement between the lines. The continuous lines are the pore pressures from the piezo cone, and then the flat dilatometer, these little dots. And you can see that's a very, very nice match for most of the profile. Again, some little problems here with some probably desaturation or not fully saturated elements, or perhaps sandy layers, but not shown so in the P naught. So perhaps we could use comparison like that to detect zones that are maybe fissured even. You know, maybe it's the degree of fissuring, because I think the work that John Powell's done at the Building Research Establishment has shown that in fissured materials, like some of the Brent cross sites, the London clay and the Gault clay that are fissured, you start getting negative pore pressures. And frankly, I think that's a flaw in the pore pressure measurements of the piezo cone. So the dilatometer doesn't have that problem. Okay, and now let's compare the cone tip resistance, which are, here's two soundings, some squiggly lines there, versus the P1, which is the expansion pressure off of the flat dilatometer. You can see that we're in the soft clay down here. You can see that it's quite a bit larger now than it was when we looked at Amherst. At Amherst, cone tip resistance was barely above the value of the P1, but in this case, it's a good 50% greater. And then I took this out of Nash et al. Because the Bothkenner clay site is a fairly famous one. They have so many other tests, and so now we can see here's cone tip resistance is in fact a bit bigger than P1. And again, the pore pressure measurement, U2, is very, very similar to P0. So there's some very strong similarity between those two readings. There's something different about those two. Can we use that to our advantage somehow in site characterization? Well, first thing I did was I did some statistics just looking at the P1 versus P0, and of course they're somewhat close together here, the factors, and you could represent that by I sub D, and that's what Silvano did 20 some years ago now, huh? So that would explain that. Here's the P0 comparison with UB at the shoulder. And you can see here in each case, these are very, very close to 1. I mean, it's a near 1-to-1 relationship, P0 to the shoulder pore pressure measurements during penetration. And then now we start seeing the difference here. Here's P1, the expansion pressure, versus cone tip resistance. And I have 3 different factors at 3 different, these are all very soft clays. There's a table in the paper. They're very soft clays with OCRs of about 1.2 to 1.5. The plasticity index won't explain it because that's fairly lean clay. That's a Varv clay, and that's a fairly plastic clay. So that doesn't really explain the differences. So I put the table together. I think what the difference really is in the frictional differences. And again, one of the reasons I picked these 3 sites was because I know Amherst has a very, very low effective stress friction angle. Don de Groot has published recently in the Singapore conferences a nice overview paper with Alan Luttinger. It's about 20 to 22 degree friction angle. You can convert that to the critical state parameter capital mu, which is 0.85. It's the same information as 22 degrees. Evanston's sort of an intermediate one. We had a big Geo Congress meeting there, prediction symposium in '89. It's about 26, maybe. I talked to Finno the other day, maybe 28 degrees, he says, his latest set of tests. But Bothkenner's got a fairly high frictional response. We're talking about the effective stress friction angle of the Bothkenner clay. It may actually even be higher than 37 degrees, but what I wanted to do was span it up, not just cluster a whole bunch of dots there right around 30 degrees that probably a lot of you might assume is the friction angle of sand 30 degrees, but in fact, it could be 20, 30, or 40 degrees, depending on what clay you're in. So I said, well, maybe that's the trend then. So I take the ratio of QT to P1, and that's increasing as the friction angle is increasing. So perhaps there is a way of using perhaps some of the cavity expansion theories that High-Sui-U has come up with. Alan Luttenegger's done that. I know we played with that. A way of interrelating that, but showing the difference in those readings because of the friction, the effective stress friction of the material is actually different. And then just to see if there was some truth to that. When I was up at Cornell doing my own PhD, I built this large chamber. I mean, this is the kind of stuff Fred Colhowie will make you go through when you want to do a PhD with him. Large chamber, 1.5 meters in diameter, 2.3 meters high. It took 6 months to fill that with clay slurry and then pre-consolidate it to 50 kPa. Then we unloaded it and did some testing. And the first set of tests, I'm going to show you the miniature piezo probes. These are actually separate soundings, a miniature cone that actually Wayne Clough built with Brian Sweeney back at Stanford, and then 2 piezo probes that I built at Cornell there. Here's a U1 element and here's a U2. Well, I put that in my PhD dissertation, but it turns out on all the deposits, we did something like 26 deposits of clay up there in the Cornell lab, and we actually ran dilatometer tests. In fact, John was kind enough to sell me a used blade for $600, and then for another $200, I built my own little readout. So for $800 back at Cornell, I was in the dilatometer testing business, the cheap graduate student version of the dilatometer. Don't tell Silvano because he'll be upset he's not making enough money on that. So let me go back and now compare that. Look at that. That's a really nice agreement with my U2 readings there and my P0 from the DMT. That's near the one-on-one. There's some scatter in there, of course. There's actually some separate soundings. And then here's the P1 reading here and the trend for that, and then here's the cone resistance. So now I have a set of sort of data on synthetic clays, and I could put that now as a fourth point on this diagram. So maybe this is structured materials, and maybe this could be considered sort of artificial or remolded materials, but it's kind of still in that trend there. I don't know that that's the highest quality data because it was back a few years. Okay. So what can we say about this? Well, perhaps there's some similarity here between the P0 reading and the pore pressures measured on a standard piezo cone. The piezo cone pore pressures, of course, are affected by saturation problems. If you haven't done a good job saturating the element with the right kind of material, maybe glycerin's the best. I know Vertec uses silicone oil, but we may actually have desaturation problems due to natural fissuring and crust, and P0. The good news is P0's not really affected by that. So we generally see that cone tip resistance is a reading that's greater than or equal to the P1 reading, and it seems like that could be, with more investigation, might be affected by the effective stress friction angle of the material. In fact, I'm thinking maybe by using coupled CPT DMT soundings, and I guess we mentioned several of the authors mentioned that already, that putting the 2 sets of data together may help us solve a very complex problem, and that's the site characterization of very, very old materials that are sort of defy characterization. So, but I'm hopeful that maybe this ratio here will help us hone in on phi prime, which I think is a very fundamental property of the material. Let me make a little plug here for Geo Shanghai. That's coming up here in June. There's some keynotes by Jim Mitchell and Harry Poulos. We have 8 geotechnical special publications. That's at 3,000 pages. That might be a record. I'm not sure there. We have a special session honoring Mehmet Tamai, who's done a lot of in-situ testing. I personally want to try the maglev train because I think that's the only one floating around right now. And then if you look at the APE, American Pile Drivers Association, they have the largest driven piles in the world going on there now. 40-foot diameter open pipe with 10-inch wall thickness. So that's going to be pretty exciting. So I'm going. How about you? Shay Shay.
Do you have any questions for Dr. Main?
If you don't have any questions, do you have any answers?
Your first conclusion is applies only to soft clays. The U0 equal to P0.
It could. The earlier study we went into the stiffer clays, and yeah. But I think as you get into fissured clays, the pore pressures start going negative. So now we have a problem. I think it's a flaw with the measurements. I think it's a flaw in the measurement because on the piezo cone we have at the shoulder. We push a probe into the clay, there's a zone that gets influenced by that penetrating probe. And we've done work to explain that using, say, cavity expansion, although strain path method would be great too. But then there's also a zone that's very, very close to the surface of the cone penetrometer or the flat dilatometer or the pile foundation, and that's a high shearing zone. And that fits in with what Imperial College Richard Jardine has shown with their highly instrumented Imperial College pile, that there's a heavy-duty shearing right up next to it. So the measurement is taken right at that interface. So it's sort of a soil structure interface problem, and it's hard to separate out those two factors.